Well, thank you for pointing that out. I've just been talking to myself this entire time. All right, let's start again then. You can tell I haven't streamed in a while, given I can't work out even how to make myself audible. But thank you very much for pointing that out. There's a few second delay between what I talk about and what I see in the comment section. So forgive me if I take a bit longer than expected to get to your comment. And since you probably didn't hear it before, let me show you Dazzle again and her lovely purring. So she'll just be hanging out on my lap, maybe messing around with some things throughout the stream. So I'll re-explain what I just explained before, since no one heard me. Like all good plans, my plan for this stream was completely ruined as soon as I started trying to do it. And the reason it was ruined was because my plan was to take data that we get from the Transiting Exoplanet Survey Satellite, or TESS, which is a telescope in space, and use that data to look at some stars. Some of them I've stumbled across which look kind of interesting to me at least, so I wanted to try and model them and get to know them a little bit better. But that won't work because my code relies on this thing here called TESS. So the way that TESS works is it takes enormous images of the sky very frequently, and if you take the enormous image, it's kind of tricky to do any science with, so it's much nicer to cut it out into smaller chunks so it's more manageable. But the trouble is that this tool TESS, which is run by MAST, which is like the big data archive for astronomy, isn't working today. So what you'd usually do is put in your coordinates of the object, how big of an image you want. So I wanted a 90 by 90 pixel image, and then you just click download if I cut out. But what will happen is that this will think for a while, and then it will eventually give up in what it's doing. So we can't do that, which means that the stream will be more me trying to work out what I'm going to be doing and answering, of course, any questions that you have. And more questions, the better. And I should, after explaining myself, turn on some nice background music, because that's always helpful, for me at least, when I'm working, is to listen to something else in the background. And that a good thing to listen to on, for me, a Saturday morning is some nice calm jazz. So let me know if the music's too loud or anything like that. And I thought maybe to start with, let's talk about the image I had in the thumbnail for this. Although I might need to recycle it in the future. So it's Hubble's 31st birthday image. So you might have seen in the past years that Hubble has lovely images to celebrate its birthdays. Hello, thanks for joining the stream. This music's in fact too loud for me, so give me a moment to lower this and maybe raise it a little bit for the rest of you. Okay, hopefully that's okay. Let me know if it isn't. So this image is really cool. It's of a very unstable star in our own galaxy, reasonably far away, but not too far, of course. So this is called AG Carinae, and it's what we know as a luminous blue variable star, which means it's a very massive star, many times the mass of our Sun, and because it's a super heavy star, it has a relatively short lifetime. So our Sun will live for around 10 billion years or so, but this type of star, this heavy luminous blue variable, will only live for a couple million years. So this one is getting on, and as they go through their lifetime, they'll emit, or they'll become unstable at certain points and chuck out a whole bunch of material. So this image from Hubble shows us the big bright star, which is about 1 million times brighter than our own Sun. and then all of this other awesome stuff around it that makes the nebula. So this nebula is about 5 light years across. So if you were to put it into some kind of context, it's the same distance between, if you could put like the sun on one side, and then Alpha Centauri would be somewhere around maybe this part. So the distance to our nearest neighboring star system, Alpha Centauri, is around about 4 light years away. So this object is actually larger than the distance between the sun and Alpha Centauri, which is pretty amazing. And you can see some really nice features in this, like all of this weird stuff that's being sculpted by the winds of this very bright and massive star. So it's a really cool photo. I like this one. I guess all of Hubble's pretty photos are pretty good. So unfortunately, we won't be looking at any nice photos like this today, because that's not where TESS's specialty lies. TESS is good at doing time series. So we don't get lovely images like this Hubble image, but we get lovely images through time. So we can get a great time series to see how something changes and evolves with time. So I guess let's look at some code. Remember, if you have any questions, just leave them in the comment section, and I'll try my best to answer them. And the more distractions you have for me, the better, since my plan for this stream completely fell through. Okay, so let's first look at something that perhaps makes a little more sense. So let's look at this thing here. So luckily I downloaded some data, or at least I thought I did. I downloaded some data before the Mars services kind of stopped working. So what we have here is a pretty simple script which uses some functions that I made to analyze data from TESS and make it super easy to do so. So all you need to do is just hit enter a few times, and then it will go about its business and do the calculations that I want it to do. So we just need to wait for it to run. And there are a few steps that happen here. One of them is it needs to find all of the stars that are in the image. Another one is it needs to correct for all of the Earth and Moon's light that gets into the TESS images. And then it also needs to align the images. So you need to put them, they're kind of close together, pretty well aligned. But there's small differences that will really mess with your light curve at the end. So you need to align them as well, and then do some difference imaging. So then you get out something that looks like this, which looks okay. It's not the best. There are things I probably need to do to improve this a little bit. But what we have on the left is the light curve. So you can see this kind of green or blue points here. They go along and then all of a sudden they go up higher. So this is just telling us that this patch of space that we're looking at, nothing much was happening, and then something happened. Which is good, because a supernova was right there. And this is a really cool supernova, because we're getting close to finishing a paper on this object, where we actually used the Hubble Space Telescope as well to take observations of this object. And so there's a really cool synergy between Hubble and TESS. And on the right hand side here we have the image. So I said that TESS doesn't make such pretty images as Hubble, and you can kind of see why here. This looks a bit messy, but that's kind of unfair, because this is the difference image. Cool supernova. Yeah, you're very right. It's all supernova are quite hot. I think this one's like, oh, let me see. Sorry, if you hear some popping noises, those are my Slack notifications. So I'm just keeping that open today because we have some abstracts due that I should keep an eye on for a conference coming up in August. So let me quickly see how hot this supernova actually was, because it was pretty warm. Actually, yeah, so let's almost there. Okay, so this was about 7 or closer to 8,000 Kelvin. So a Kelvin is pretty much a degree Celsius plus 273. So it was pretty warm. Dazzle's on the move again. I'm not sure if you can see or hear her, but she's decided that turning around is the correct thing to do. And now she's messing with them. Nope, okay, she's going. Alright, well that was a nice brief visit by Dazzle. Okay, so what I was saying before is that this image on the right is a bit of a bad one to compare against Hubble. Well, that's not how you spell. So instead, let's use this. Okay, so what I'm showing here is just a single image from yeah, 7 to 8,000 Kelvin. I think would be pretty warm for anyone. So what we have here is a single image from TESS. So if this were Hubble, it would look much nicer than this. And in fact, let me see if I can bring up a comparison. Oh man, I always forget the coordinates of these things. It's too hard to remember. Too many numbers. Okay. So this is what TESS sees. And now let's go over to what Hubble sees. Let's just do a good old Google image search. So this is... Oh, that's not going to work. Oh dear. Wikipedia is always there to save the day. Okay, so this is what Hubble sees. Lovely, beautiful galaxy. But if you were to look at it in the exact same galaxy in TESS, nope, that's not it, that's not it. You just see this blob. This kind of blob here is that exact same beautiful galaxy that Hubble sees. So, you know, TESS isn't there for beautiful pictures. It's there for this time series of images, which are very, very useful. So, that's that. Let's look at perhaps what I want to try and do on the stream now. So let me go to a different supernova, one called 2019 VXM, and look at the rise. Okay, so what do we have? Oh no, maybe I didn't download this one. Let's see if it works. Yeah, this might be a bit of a tough one. Maybe every one of my plans is kind of shot through. Which also makes it hard for me to actually do work if I can't even access data. So hopefully they make MAST accessible again soon. So I have a feeling this isn't going to work. So that's a bit of a pain. While I'm thinking of maybe something else to try, do you have any questions about anything or anything that you would like my thoughts on, or even aspects of my work that might be interesting? Hey, thanks for joining the stream. So I think this is probably the most viewers I've had on one of these streams. That's pretty cool. So thanks for joining. It's just a shame that nothing actually is working this time. Oh, that's very kind of you. Sleep is always useful, but learning, that's where the true purpose of life comes in. So since you're staying up, you should ask me a question. I should give you some good pieces of advice. Maybe explain TESS. That's a very good point. I should do that. So let me just let me bring up TESS. Nope. Oh, you'd think I would have learnt by now. Alright. Okay, so first lesson, just searching TESS doesn't work. You need to put TESS Space Telescope for you to get images that are related to what you're supposed to be doing. And that's not the first time that's happened. Every time I want an image of TESS, this happens to me. I'm a slow learner. So, let's see if this image wants to be full screen. It does, good. So TESS is a really cool telescope. It follows on from what was done with the Kepler Space Telescope. So Kepler was launched in 2009, and its purpose was just to stare at a patch of space continuously and try and see if there are planets in that patch of space. Which is a very hard job to do, but Kepler did it fantastically. And in 2013, Kepler broke quite a bit, so it ended up doing something else. It started pointing at different patches across the sky. And by doing this, we were able to look at a whole lot of different stuff across the sky, which was great. We found a lot of cool supernova, or said that again, a lot of nice supernova. There we go. That's more correct, I guess. And we did a whole lot of cool science with it. But Kepler died completely in 2018 or 19. I can't remember. Must have been 18. It was just short of 10 years in space functioning. So it died, but that was okay because the replacement, TESS, the Transiting Exoplanet Survey Satellite, was ready to go up into space. And it was launched, and it did pretty well. It's a great telescope, and it has a lot of advantages over Kepler, but also some disadvantages, of course. So TESS is a relatively small satellite. It's about the height of a person. So if you're a person standing next to this, you'd measure up to it quite well. But it has, instead of a mirror and a single camera like Kepler did and lots of other telescopes today do, TESS has 4 separate cameras which use lenses. So you can see here in these dark regions, 1, 2, 3, 4, those are the 4 cameras of TESS. So the way they're aligned is that each camera kind of takes up from when the last one left off. So they tile the sky in a big long strip. And this patch of sky that they image is absolutely enormous. It's over 9,000 times the size of the full moon. So it's a massive patch of sky. And it takes, or at least in the beginning, it took an image of this massive patch of sky every 30 minutes, which is amazing because generally telescopes only take, say, 1 image of a patch of sky every night if you're lucky, or every couple of nights for surveys. So you miss out on whatever happens between the 2 images. But for TESS, if you're taking an image every 30 minutes, then you really get to see things that change quickly. And now TESS is actually taking images every 10 minutes, so that's even better still. We could potentially find things that are super fast and only last, say, 20 minutes or 30 minutes. So that's awesome. So this is where my interest in TESS comes in. So I don't really care so much for exoplanets or for stars. They're more of a passing fascination for me. The main thing I do is look at exploding things. Okay, thanks for joining, Sausage Jockey. It's always a pleasure to see you. What was I saying? Sorry, I get easily distracted, which probably isn't a good combination for streaming and having live comments. But anyway, so I don't care about stars or planets, I care about exploding things. And for me, the most interesting type of exploding thing is something that explodes really quickly. So, supernova, they've been known for decades, and we know them relatively well. There's still a lot of really cool science that we can do with supernova, which is nice, and I'm working on that kind of stuff. But for me, the most exciting part is the exploding things that we haven't seen before. So I mentioned that normally telescopes take an image every couple of days. But if you wanted to find something that explodes and disappears in, say, an hour, then you pretty much have no chance of ever spotting them from observatories on the ground. TESS at the moment is the only way you could actually do this. So what I'm most excited about is doing a blind search through all of the data from TESS to try and find out what's happening in the night sky that we just haven't seen before. So this is like a total gamble, right? Because I have no idea what could be there. We have some ideas on the timescale of a couple of days, but as for hours, that's kind of an unknown. It may not even be that there are phenomena that live in an hour time zone. But you have to look before you can say one way or the other. So that's what I'm building towards with what I'm doing. But it's pretty tricky. TESS data is really messy. Yeah, it is an awful lot of data to go through. So I forget exactly the numbers. So TESS looks at a sector, they call it, for about 28 days, and taking an image every 30 or 10 minutes over those 28 days of an enormous chunk of sky makes a lot of data. I think it's around about 1 terabyte to 2 terabytes per sector. So, it's a lot of data to go through. And you need to deal with all of the idiosyncrasies of TESS data as well, which can be a challenge. So in this image as well, we have the Earth and Moon quite prominent in the image, and that's no real mistake because TESS orbits around the Earth in a kind of elliptical orbit that's in time with the orbit of the Moon. So 28 days is kind of how long it takes the Moon to orbit around the Earth. So TESS is actually in kind of a resonance orbit with the Earth and Moon, which makes it extremely stable. It can stay in its current orbit. I think the last estimate was like 10,000 years or something ridiculous like that. So its orbit is under no threat of decaying, which is amazing. But that means that sometimes the Earth and Moon get in the way of the detector and create a lot of mess that's hard to deal with. So let me see if I can show you why that's a pain. Okay. So TESS points everywhere. So the idea of TESS is that you want to tile the entire sky. So Kepler had a very focused look on the universe. If you imagine like cones stretching out, Kepler was a very precise cone at a particular patch in the sky. But TESS is like it's more of a shotgun approach. Kepler was a sniper firing on its targets, whereas TESS is just shotgun. It'll get everything that's bright and close. So they want to find all of the closest planets. So it should be able to do that. What kind of explosions are theorized to be found in this short time frame? Very good question. So supernova are powered by thermonuclear processes. So that thermonuclear process has a characteristic time frame, and I think the time frame for that's like a week or so. So if you are seeing something that rises and disappears in the space of even just a couple of days, then it can't be ruled by, or it shouldn't be ruled by thermonuclear processes, which is the process of slamming atoms together, or sorry, rather atoms decaying and producing lots of energy. Well, I guess the full explanation is atoms get slammed together, they make heavy isotopes which then decay and then provide you with lots of light. So for things that are in the very short time frame, they have to be much more energetic or have some weird things going on. So things like kilonova, which you get from neutron stars colliding together, they also only last a few days in optical light, but that's mainly because the ejector, the stuff that the neutron stars make when they collide, blocks a lot of the optical light. So in the short time frame, you'd expect to find relativistic processes like gamma ray bursts, which we found the first one of those in TESS sometime last year, and I did a short video on that, I think maybe a week or two ago. So if you want to learn more about gamma ray bursts, check that video out. So it's just kind of like really extreme processes. Which is kind of why I'm interested in this, because if we find them, there'll be great tests for kind of on some scale fundamental physics to see how these things actually get their power. Yeah, so TESS's orbit is, because it's so incredibly stable, an alien species could come here long after humanity's been wiped out, perhaps, and still find TESS orbiting around in its orbit. I wonder if it will still be taking data then. So far it's been doing okay, but Kepler lasted a decade, and probably could have gone longer if some things didn't fail. So it'll be interesting to see how long TESS can survive for. Okay, so I mentioned the extreme background of TESS, so let me show you. So if you're wondering what I'm using here, this is Python. A lot of astronomers use Python as kind of the main programming language. And this environment that I'm coding in is called Jupyter Notebook. There are lots of different IDEs they're called to edit in, but I've become used to Jupyter Notebook because it has all of your thoughts in a straight line, which it can be good, but also can be a massive pain. Test.background, and I think like 600. Okay. Huh. That's not as nice as I was hoping it to be. Yeah, that's better. Okay. So here we have the TESS background image, which my code goes through and calculates. So you imagine this being overlaid on top of this. So one way to put in perspective why this is a problem is to look at the values of how bright things are in this image. So if we just pick a random star, say around here, the bottom right-hand corner of this plot tells us how the value of that pixel, and that has a value of about 50. Yes, of course, ask any random question you want. That's fine by me. So, the star has 50 counts, we call it. And if we go around here, the background has 8.4 times 10 to the power of 3. So, almost 9,000, or I guess close to 8,000 counts. So, we need to remove 8,000 counts really precisely to make sure we actually recover something that's only as bright as 50. So that's pretty challenging to do, and that's taken me the better part of maybe 2 years to actually work out how to do this precisely. But luckily we've worked through all of that now, so it's relatively working okay. We'll see how well it really does. So I'm still waiting for that question. I do like random questions. But while we're waiting for that question and any other questions, let me show you another cool supernova that I'm supposed to be working on. I think this will probably just end up being a show and tell. Sorry, it's probably not as exciting as actual science happening, but there's not so much I can do if the data archive is busted. Okay, so this supernova 2019 VXM is pretty cool because we have a whole lot of data on it. If Jupiter was a supermassive black hole, how long would the Earth survive for? It depends. How massive are we making this supermassive black hole? Is it I guess it must be much larger. Well, I guess the immediate answer is instantaneously. The Earth would die because the radius of a supermassive black hole is several times that of, or it can be several times that of our solar system. So if you put one anywhere in the solar system, the Earth would immediately be consumed. So we wouldn't last too long. But if you made a Jupiter-sized black hole and put it where Jupiter is, then nothing would change, effectively, and everything would be fine. The only thing that would change is that we would have a really nearby cool laboratory to test extreme physics. I mean, how incredible would that be if we just had a black hole sitting in our backyard that we could go to and test general relativity? We could probably see from Earth if Hawking radiation were true, and therefore validate or disprove Stephen Hawking's greatest contribution to science. And, everything else. We could test general relativity to make sure it really works. And it'd probably be a lot easier to get an understanding of how quantum mechanics and general relativity play together. So maybe one day, if we're lucky, a friendly black hole might turn up. Another random question. Have you read Space Odyssey 2001, the book? I haven't read the book, but I've watched the movie and I've read 2010. Both of them. The movie was fantastic. I think the main differences between the movie and book are that in the book they go to Saturn, whereas in the movie they go to Jupiter. But 2010 is pretty interesting as well. I also got 2100. I think that's what it is. Like the sequel to 2010. I still haven't read through that. It's been years since I got it though. So maybe one day I'll get around to reading it. Okay, next question. Does phenomena of disappearing socks in the washing machine prove multiple worlds theory? I think you're probably onto something there. I mean, like, some socks, they're around forever. You never have any problem, and suddenly they're just gone. So what changes? Well, I reckon there's a good chance that, like, a micro black hole just pops into existence, and then absorbs everything else, and then pops out of existence again thanks to Hawking radiation. But, I have no idea where those go. Somewhere there's just like a big stockpile of socks. I'm glad that seeing from the inside perspective is somewhat interesting. Be careful. Yeah, I should be careful with wishing for a black hole to pop through. Yeah, I wish the archive wasn't taking a nap though. That would be more helpful for the stream. But I don't know. If it's always fun answering questions, I feel. Or at least it's fun for me. What are my thoughts on theorized black hole edge of our solar system? Yeah, so that's a good one. So, there is growing evidence for a massive object in the outskirts of our solar system, often called Planet 9. Though we of course don't know for certain that it is a planet. It could be any object that's sufficiently massive. So we think that... So I guess let me explain why we think a planet is there. So everything with gravity interacts with everything else, right? So if you're orbiting around the sun, you're being tugged on by everything else. The sun is the major component, but everything else that has mass also influences how you orbit. And what we've seen in the outer part of the solar system is that there are a bunch of objects that seem to have similar orbits, as if something else has come through and forced them into that same kind of orbit. And the best explanation for that I've seen is that there's something like an 8 to 10, an object that has the mass of between 8 or 10 Earth masses, flying around in the outer part of the solar system. Well, going pretty slow, I guess, relative to around the sun, and shepherding these objects into particular orbits. And just a week or two ago, there was another paper that came out that showed us that, gave us some more indirect evidence for a planet 9, where, so this might be a little bit complicated, and I might not do the explanation justice, but in the solar system we have, let me just see if I can, let's just get an image of the solar system, so there's at least something relevant to what I'm talking about. Okay, so all of these are terribly not to scale, right? So don't get fooled. Okay, this one has a disclaimer on it, so that's good. Come on. Give me your image. There we go. So, all of these objects orbit around in a plane. We call that plane the ecliptic. And naively, you would assume that, based on how solar systems form, you would assume that the ecliptic, this plane that all the planets and stuff orbit around the sun on, would orbit around the equator of the sun. But this isn't the case. The ecliptic is tilted by, I think, it's either 6 or 9 degrees from the equator of the sun. So it has an inclination, it's tilted. And people weren't too sure why there was this tilt. Some ideas were perhaps when the sun was forming out of a nebula, other stars would have been forming around it, and as these other stars passed close by, they might have distorted and warped the disk that was forming the protoplanetary disk, the disk that forms planets, and then that gives us our offset from the equator of the sun. But this other paper that came out recently in argument of planet 9 is that if you have a massive planet that's super far away from the solar system, it has a big impact on the solar system over time. So it's like levers, right? If you have a very long lever, it's easy to lift something, and if you have a massive object at a very big distance, it's easy to change the orbits of the inner planets. And from their simulation, they actually found that if you included planet 9, then you could quite easily remake the inclination of the ecliptic that we see today. So that was pretty cool. There are searches to try and find planet 9, but we haven't found anything yet, which is a bit unfortunate, but it'll be very hard to spot if it's there. That was probably a long-winded explanation. Hopefully that makes some sense. Alright, let's see. Yeah, I read the second book first with Space Odyssey. Dark Matter. I'll come back to that one maybe. This is a good question. Why are some of the sky surveys only available for specific science institutes? So this is, I guess, it's a changing culture, which is good. In the beginning, everyone was very protective about their stuff, which is good, good enough, because back, say, like even just 10 years ago, there was still a limit of the amount of data we had. So if you wanted to have, you applied for grant money and you need to make sense, or you need to reach the goals that you said you were going to reach, then it makes sense that you need to hold on to your data and get everything you can out of it before you eventually make it public. So there would be like several years between when the data were taken and when they were made public. But now it's kind of turning out that there's just way too much stuff. Like, we get way too much data now, so there's no way any single person or single collaboration can sift through all of this data and get all of the results. So the culture now is much more open, that various programs will just make it all freely available. And there's a really cool tool. Let me see if I can... Nope, not that one. What's it called? I always forget. Data archive. I always lose where it is, but there's a really cool tool that is hosted by the Space Telescope Science Institute. Here it is, the Mars portal, where all public observations that have been taken by Hubble or anything else are just available here. So it's getting better, and we really are in the era of big data. But I also think a a big part of it is that people are just more willing to collaborate with one another now, which is great. But there are still some surveys which lock themselves off. But generally, at some point, they'll make it more public. So going back to the Planet 9 question. So the Planet 9 black hole kind of connects with your wish. Yeah. yeah. So if instead, so the leading idea at the moment is that it's like a Neptune type planet sitting out in the outer part of the solar system. But if it's a black hole, then that would be far more exciting for, I think, everyone. Where was I up to? Yeah, you're exactly right. The orbit of Planet 9 can and has been calculated by models. So when they search for Planet 9, they aren't doing a blind search just across the entire sky, because that would take forever and probably be impossible. But if you use these models to inform where you should look, then you have a much greater probability of actually stumbling across it. So just as I was talking about the data access before, this is the public data that we have for this galaxy here. So they're all overlaid on top of it, and it's a really cool tool. Like, you can see all of the different things. We have TESS that's observed, of course, Swift, Spitzer. There will be Hubble observations here as well. 3Pi, that's Pan-STARRS. I don't know what Calcos is, though. A black hole lensing telescope inside the galaxy. That would be really cool. Yeah, so this is a really, really great tool, and shows to some extent that astronomy is becoming more open source. How long has observation time on J? Oh yeah, that's a good question. So actually, the way JWST breaks down, let me get a picture of that. Let me try and at least have something relevant to what I'm talking about. Otherwise, it's just a weird distraction. So I'm sure many of you know what web looks like anyway. Oh man, why does it always fool me like this? Where is a good one? Where is a good image? There we go. Good. So we have our Webb image. So Webb is a really cool telescope. It's super complicated though, as you've probably heard. So down here we have a sun shield, which blocks the sun, which will be somewhere down here, shining up and getting into the telescope. And it also thermally isolates the telescope from the sun. So light from the sun will heat up the telescope, and because this is an infrared telescope, you really don't want that happening because it'll just mess up your detectors. So this shield is crucial to making sure that TESS works. Oh man, too many space telescopes. Crucial to make sure that JWST works. So light comes in from some distant object, bounces off these, I think there's like beryllium-plated mirrors, and then down through this little hole in the middle here and goes into its cameras. So as for time, oh man, I'm getting them all confused. JWST has a few core programs which are already guaranteed time, but then it has the rest of the time is just free for all. And so far as I know, only the first year of time has been booked out. So last year in November, maybe October actually, was the first round of proposals for JWST. And luckily my group got a few of those proposals through. But yeah, each year, the way telescopes work is that they'll call for proposals, everyone submits their proposals and sees if they get time to do the science that they want to do. Where was I up to? JWST, okay. do think planet Earth is being observed by unknown extraterrestrial intelligent alien life? I guess this might sound strange, but I really hope so. That's not like my scientific opinion. That's just my personal. I hope that's the case because, you know, I like all astronomers. I think I hope to think that we're not alone in the universe, and I really hope that there's a way to travel through the universe really quickly. So, if we do find intelligent life, then maybe that will show us that these things are possible, and it will help us discover these things for ourselves. That sounds like I guess it might be Friday night for you, so that sounds like a good plan. Is a black hole at the edge of the solar system very difficult to justify? It would mean that it would had to come after the solar system was formed. Yeah, so that's a very good point. So there are multiple problems. One problem is, how do you make a black hole that is only, say, 10 times the mass of the Earth? That's really hard to do, I think. One argument is that it's a primordial black hole, where these things would have formed at the beginning of the solar system. Oh no, not solar system. I mean the beginning of the universe. But and then one just so happened to end up orbiting the sun. I think that idea is not so likely. But yeah, having a black hole at the edge of the solar system orbiting the sun is unlikely, because if it were from a massive star that turned into a black hole, we probably would have seen evidence of the massive star existing in the past and the surrounding environment. So as much as it would be cool, I don't think there would be a black hole at the edge of the solar system. There's no evidence of intelligent life on Earth. Yeah, it seems to be that case sometimes. I haven't read the Culture series. I've been meaning to, though. You might have seen a recent video I did with my brother on like the first science fiction. So the reason I wanted to do that is I wanted to give myself a reason to start reading through science fiction again. But I've only heard good things about the Culture series, so I do hope I get around to reading it one day. Oh yeah, I don't talk about myself too much on my channel because that's the most boring thing that anyone could listen to. Where I work and study and main focus, yeah. So at the moment I work at Johns Hopkins University, which is in Baltimore. So that's where I work, but physically I'm in New Zealand at the moment, which is a nice change of pace. And my main work is just around explosions in space, pretty much. Or at least that's the goal, but the last year I've become more and more focused on calibrating telescopes and understanding the data that we're getting. So before I showed... so this line here, this single line of code here, took me probably like 2 years to get to. Behind this is a whole lot of junk. Let me show you just how much junk sits behind that one line of code. So this is my Python module for TESS reduce, the package I made. So all of this goes into that one line. So it's, how many lines is it? So we have 1,800 lines in this script, but this isn't all of them. We also have catalog tools. There's 300 lines in there. Calibration tools, and close to 500 lines in there. And I think 1 or 2. So there's like a couple thousand lines of code that go into making one line of code work. Where was I? Let's just have web here. Web's always good to look at. Yeah, and the one of the things I'm working on at the moment is, so if you have telescopes, we have telescopes all around the world and in space, and they all take images of objects. How do you make sure? Add comments to the code. No, I will never. I made a joke about this a few days ago, or maybe like last week or something on Twitter, where I was going through my old code, and of course I haven't commented it, so I was like, what does any of this do? So, and it occurred to me, by not commenting my code, I'm living the truest embodiment of science. I have to peer review my own code every time I try and add anything to it. Yeah, you're right. There are some parts of the code where it's like, I have no idea what I was thinking at this point, but I guess it works, so it's fine. Not as bad as Perl. Luckily, I've never used Perl, but I've heard shocking things about it. One of the really serious image reduction pipelines my supervisor has spans like 5 different languages, because he like wrote it over the course of a decade or something like that, where all these languages were changing. So it was like, I think there's Fortran, C, Perl, Python, and one other one. So he's super hesitant to actually go in and check out the guts of the machinery, because there are just too many conflicting parts in it now. I am making lots of work for my future self, but I guess I accept that workload by being lazy. IDL, yeah, I think that was the last one. So that was the 5. Fortran, C, Python, Perl, and IDL. And Perl is his least favorite part of that code. Thanks for the comments on enjoying what I do. It's always great to see people actually learning from me just talking to myself. What can you see of the Milky Way from New Zealand? You can see all of it. The Southern Hemisphere is... I'm probably very biased because I grew up in the Southern Hemisphere, but the Southern Hemisphere has the best skies. No doubt about it. Let me see if I can get a... let me see if I can actually show you a photo I've taken. Every now and then I play around with some astrophotography. Never too serious though. And the last time I took some spacey photos was a long time ago. A long time ago. Sorry, I can't see any comments you're leaving at the moment, but I will check back again in a second. Maybe I can't find them. Oh, whatever. Alright, we don't need to look at that. There are many other better photographers out there than me. So let's see if we can grab one of their works. So actually, there's one I have in mind now. So as the case, you can't find the thing that you want to find. Okay, this one's good, pretty good though. Who is the photographer for this one? Does it say? Okay, so this one was taken by Y. Beletsky. So this is a lovely photo. So this is the Milky Way. Somewhere down here is the center of the Milky Way, and that sits high above the sky during winter, which is great. Up here is something we call the coal sack, which is an absorption nebula sitting up there in the sky. And right next to the coal sack is the Southern Cross. So this star, the star, the star, and this star make up the Southern Cross, which is a pretty important constellation in the Southern Hemisphere because we can use it to find south, which is about here. These two stars here are what we call the pointer stars. They point to the Southern Cross, so we can find it easier. But this one here, the slightly brighter of the two pointers, is Alpha Centauri, which is the closest star system to the Earth. And then, I guess the best things of the Southern Hemisphere are these two blobs here and here. So this is the Large Magellanic Cloud, and this is the Small Magellanic Cloud. And they're two dwarf galaxies that are slowly being eaten up by the Milky Way. So if you go find a nice dark place in the Southern Hemisphere, then you can see all of this cool stuff. And then these pink patches are, I think, H2 regions. So they're where you have, I think it's star formation going on. But yeah, so this is taken from Chile at the Very Large Telescope, which is run by the European Southern Observatory. Yeah, Rocket Lab. That's really cool. It's awesome to see New Zealand actually somewhat involved in space these days. How far away are TESS observations? Are they only in our galaxy, or are they thousands of light years away? So it depends on how bright the object is you're looking at. So for the most part, TESS is only concerned about stars within our galaxy, and of that, close stars. So stars that are maybe tens of light years away from us. But for me, and other astronomers like me, that look at very, very bright exploding objects, we can see them millions of light years away from us, which is very handy. Yeah, so it really depends on how bright the object is you're looking at. I have an idea of a video that I'll eventually end up making, which is how far away can JWST actually see. So that one should be, when I get around to making that should help answer that question as well, because Webb can see very, very far away. Yeah, the Magellanic Clouds are very good to look at. There's a lot of, through a telescope, there's a lot of really cool things as well, like the Tarantula Nebula, which is inside the Large Magellanic Cloud, Omega Centauri, which is a big globular cluster, and all these other things. What's coming after TESS? That's a very good question. So TESS is probably going to be around for a long time to come. So TESS itself, I don't imagine will be getting replaced soon. But one idea that's been floated by the guy who's in charge of the whole thing is, now that they've worked out how to make TESS, it wouldn't be so hard to make a second TESS. So there was a few years ago, there was a science conference, and he just was talking about the future of TESS and these kinds of things. And his suggestion was that they make 3 more identical TESSes and launch them up into similar orbits, and then you would have an insane coverage of the sky. The amount of data would be way too much. But you would have 4 of these telescopes that look at enormous slices of the sky very quickly. And you'd quickly make sense of everything, I think. But what I would really like is a blue version of TESS. Oh, thanks for joining, Kim. So it's always good to see people learning and enjoying the stuff I'm making. Oh, good. So TESS observes in red light, which is good for a lot of applications and very good for TESS's main goal of looking for planets around other stars. But it's not so good for supernova. For me, I would much prefer a blue version of TESS that looks at blue light. So I hope at one point they make a blue version of TESS and send it up, and then that would really, really be helpful. Louvois, that would be really cool. I think it's been a while since I've read up on it, so I might be. Oh man, how do you spell it? But yeah, that's a mental telescope if this happens. It's like JWST on steroids. Let me chuck an image of that up. And look at that. It's massive sun shield, massive mirror. Really, really big. So the proposed diameter side to side of the mirror, they want either 8 or 15 meters. So JWST is about 6 meters. So even 8 meters is a massive step up, but 15 meters, that would be really good. And the cool thing is, I'm sure many of you have followed SpaceX to some capacity. Once Starship works, or if it ever ends up working, with its enormous silo size, you could launch single dish telescopes that are like 8 meters across or something like that. And then if you have folding telescopes, you could have insanely massive telescopes. So that would, the Starship might make something like Louvois actually plausible. Do you have enough computing power on hand to work through the data at the same speed as new data comes in? Yeah, to a certain extent. So far, myself and my group have been hamstrung by the working out how to process the data. But now that we're close to being able to do that, we should be able to move through analyzing the data faster than we're getting the data, which is nice. But then, by analyzing the data, I mean just making light curves, so just seeing how the brightness changes over time. Actually, processing and thinking about and doing research on each one of the light curves we get, I don't think a single human lifetime would be enough to sift through the data we have already. So, working out how we can get other people to use the data is something that we'll need to think about in the near future. What about observing gravity waves in space? Yeah, so there's a mission concept called LISA, or I think it's ELISA now, and let me find a picture of that. LISA gravity wave. For those that were here before, when I googled TESS, trying to find a picture of TESS, I learnt my lesson. I didn't just Google LISA this time. I added some space qualifier in there. So this is super cool. It's like a triangle version of LIGO in space. So you have these 3 independent satellites that will fly in a constellation, and they fire lasers between each other and measure the distances between them very precisely. They need to work out any drifts that happen in their combined orbit, but theoretically you could have baselines, so distances between these 3 things of hundreds to thousands of kilometers, which would let you observe supermassive black holes merging since the beginning of time, pretty much. So if this flies, it'll be an incredible tool for astronomy. Why is gold so ideal for infrared? I don't know that one off the top of my head. The basic answer I can give at the moment is each atom has their own preferred lights that they like to eat, different wavelengths of light they like to eat. So if they don't eat the light, then they generally just bounce it back. Those gold colors are good for infrared because they don't have strong absorption lines, or they aren't transparent to infrared light. Sorry, I can't give a more detailed answer there, but hopefully that's somewhat answers your question. Oh, joined from Alaska. That's awesome. I've never been to Alaska before, but it looks great. Have you? So from your comment, if the Northern Lights don't get in the way, I take it you've seen the Northern Lights, because I imagine that's pretty amazing. I haven't seen any aurora myself. That's on my to-do list for when things get more normal, I suppose. Yeah, Alaska looks like a beautiful place. I think ELISA is supposed to be launched sometime this decade or early next decade. It's making filter wheel for telescopes such as TESS too complicated. Yeah, so in this case it is pretty complicated. So TESS is built for precision in counting bits of light. And because they have tuned it to a specific type of light that they're looking at, their detector is built to count very well that kind of light. So if you added a filter wheel, which certainly would be possible, but it would add complications to the optical system, which would make it less efficient at counting light. So at the moment, TESS has the filters built into the lenses of the cameras. But you could imagine putting some kind of filter wheel system in there. But there's lots of optical systems get pretty complicated. And if you're going for like the most efficient system, then you need to just make a decision. But if they were to make follow-up ones, then adding a filter wheel would be pretty good. 2034, okay, that's a while away. Yeah, it always puzzled me when I was, I guess, I've been thinking about science and science education for way too long, which is largely why I like doing this, because I just like teaching and explaining things. But I was always puzzled why science wasn't more popularized, but it's getting much better now. There are so many big YouTube channels now that talk about science, and there are lots of new TV shows which go through things as well. So things are definitely getting better, and I think astronomy is a major driving force behind this as well. So it's always a great to see astronomers out there pushing for more publicity and that kind of stuff. It's not so much that we need more people doing science. It's just general scientific literacy in society is very important, as I'm sure many of us are witnessing at the moment. Yeah, so YouTube, when I was in high school and university, Khan Academy was Star Talk, that's another good one. Yeah, and good shows that really embrace science, like The Expanse, certainly help. Yeah, the new space race. It'll be interesting to see how that goes. I'm all for a non-aggressive competition between countries. But hopefully it's not just like a overly convoluted metaphor for we have really mastered missile technology and can blow you up at any moment's notice, like the original space race was. hopefully we're moving beyond that a little bit. Yeah, Elon's doing pretty good. I have concerns about Starlink, as many astronomers do, but yeah, other than Starlink, I'm all on board for everything else. Yeah, I can convince, I can say that Zast should, or I'm not sure how you pronounce that name. Sorry, too many unfamiliar combinations of letters for me. So Zats is the best I can do. You should watch The Expanse. It's really good. Missile measuring contest. That's a really good way to sum up the Cold War, where America definitely had the the largest missile there. So what else? What else can we talk about? Yeah, I think space will definitely become good. My job at convincing worked. It's the first season is not so great. I will admit that freely. Like you can really see the budget of the first season, but after the first season, the budget really starts to pick up. And then once Amazon takes over, it's got a lot of money, and it does good things with that money. For space, it almost certainly will become fueled by commerce, and in some ways that's a good thing, and in many ways probably not a good thing. But if you regulate commercial systems, then they work really well. But at the moment, especially, we're seeing so space is in the domain of kind of the global government, so the UN. So it takes a long time for the UN to come to a decision on global matters, because there are just so many voices in the discourse, which is good. It's always good to have a discussion, but at the same time, companies like SpaceX aren't bothered. They just go through and push forward, which is great that people are pushing forward, but not so great that they will end up crowding low Earth orbit and potentially changing the composition of the upper atmosphere, which would have unknown consequences for the climate and other things. And what's the other one? Oh, Stark-Kessler syndrome, which would eventually lock us in a cage of our own creation. So, in conclusion, the world is grey. Jeff and Elon do bad things, but they also do good things, in my opinion. So, they're a shade of grey. Let me see. Where was I up to reading? So we're seeing with SpaceX at the moment that once commercialization really gets hold, then things can become much better. I mean, like, NASA had the same technology and the same access to people to try and land rockets, but they just didn't, because NASA is historically risk adverse because it's a publicly funded entity, so they can't really take too big of a risk, because if it just fails, then people will be asking, why are we spending our money on this? But reusing rockets saves you money, so capitalism really kicked in there and really advanced space, so that's amazing that's happened. And the same thing, like mining asteroids in space, I think that's probably a really good thing that should happen. The less we have to mine on the Earth and damage our own ecosystems, the better. If we can just grab it all from space, then why not? So there are lots of pros and cons for all of this. Yeah, so I think you're right. It will be very hard to expand into space unless we know how to work together on Earth. Otherwise, we'll end up... That's why I think The Expanse is one of the more accurate science fictions, unfortunately, because although the Earth is united, the separate factions are still at each other's throats. So I'm not sure if or when that will happen, but real progress probably won't be made until people are more unified. Yeah, I think commerce is probably the largest motivator for space exploration now, and for good reason. I mean, like, one asteroid contains like many times more platinum and gold in it than what we've dug up from the Earth. So yeah, there'd be a resource bonanza, and the gold market will just collapse straight away. Yeah, so with Starlink, it will benefit a lot of people. So in that sense, it's great. But the other side effects, damaging observatories is one thing, which I of course not too big of a fan of, but I can live with. There are other things though. So the Starlinks are built to deorbit after like 6 months. And every time they deorbit, they burn up in the upper atmosphere. So all of the stuff that the Starlink is made of enters the upper atmosphere. So you're changing the composition of the upper atmosphere. And it's not, I don't think, too well understood how dumping thousands of satellites filled with heavy metals and things like that into the upper atmosphere will change the climate. So in that aspect, I'm not a fan of it. And there are other ways that we can do internet on the Earth, but in a lot of places, unfortunately, governments have kind of given up, and monopolies reign supreme, and all of this kind of stuff. So it's a grey issue, that's for sure. I see lots of belters in the chat, so that's good. Yeah, so hopefully we can avoid the extreme separations that we see in The Expanse. Okay. So this is, although we haven't done much science, this has been pretty fun for me talking to all of you. So let's look at this supernova. This is 2019 VXM. So this is the TESS light curve of it. So we have the rise of the supernova, which is really important to have. Then we just have some extra parts later on. These parts don't matter so much, but we have them, so that's nice. But the really cool thing is we have a whole lot of data. Oh, that's right. I messed something up. I was working on this a few days ago, and I busted it, so it's not plotting as nice as it used to. Actually, maybe I can fix that. Actually, nah, that can't be fixed quickly, unfortunately. So let's just plot it. Grid spec. There it is. Man, that's really busted. Okay. Well, damn. Alright. Sometimes computers are a bit slow. Okay, so this is the rise that TESS sees. So this is very useful for us to work out if there are any funny things that happen at the start. But then we also have a lot of other data. Coming down. Yeah. Yeah. It's the only way to code. So, as well as TESS data, we also have lots of data from another space telescope, SWIFT. And I haven't gotten around to really studying this one yet, but it should be pretty cool because the ultraviolet light is at one end of the spectrum and TESS is at the other end of the spectrum. So there's a lot of stuff that we could say about this, but I need to work out exactly what it is we can say about it because this is a core collapse supernova, right? A type 2P, and I haven't or is it 2N? I think that's actually a 2N. N standing for narrow line. So I haven't worked that one out yet. My cat is wanting to escape, so I'll be back in just a moment. Okay, back. Cat has been removed. No, sorry, I did show the cat at the start of the stream. So if you wanna wind back, she's there. I think there was even some nice ASMR pairing in the microphone. But she usually sits on my lap while I'm working, so that's always nice. Apart from when she wants to be pat, and then it's always difficult to actually reach the keyboard. I haven't actually read too much about the Artemis program, so I can't really comment on that one, sorry. Yeah, so the good comment that there will be a lot of... So Starlink is one of them, but then there are the Kuiper constellation, the OneWeb, and I think China announced recently that they were wanting to put up their own constellation. So low Earth orbit is going to become incredibly crowded very soon, which is not good by any measure. So I think SpaceX has been approved for like 40 or 60,000 satellites in low Earth orbit, which is an insane number given that currently there's like a few thousand. So it's orders of magnitude more satellites than are currently up there. So making sure that things don't collide, I personally think is going to become impossible. So I'm afraid in some capacity that we're witnessing a slow-mo car crash, where this car crash will trap us on the Earth more or less indefinitely. Yeah, the Kessler syndrome is... It's not good. Not good at all. How large elements than iron created in a supernova? Very good question. So, the way that nucleosynthesis works in a supernova is that you have big star. Big star is smashing atoms together in the center. And each atom it smashes together, it gets a little bit of energy from. But the bigger, once the atom gets to iron takes energy to smash together to make heavier atoms. So iron is often said to be the most stable element. But what happens in a supernova is that once the iron core is formed, you have no more energy pushing out against the outer layers. So the outer layers all come crashing down and bounce off the core. And in this moment where it bounces off the core, you have insane temperatures, pressures, and a lot of energy. So it's no longer about using or creating energy to support the star. Now energy is just being pumped into these atoms from the kinetic energy of all of this material that the star had been supporting, just crashing down. So when it does that, you can synthesize all manner of very heavy elements. And then the star explodes, and then those elements get spread out into the universe. And in fact, this a lot of people probably haven't heard about this. It was not obvious to me when I first heard about it some years ago that the light we see from supernovas, so this part here, all of this, isn't like heat or anything like that. It's from the decay of nickel 56. So a specific atom, a specific isotope of nickel, is unstable, it decays, and then that light is what we see. So, there's a lot of nickel atoms that get made that make these things so incredibly bright. Yeah, the intro to Wall-E, where the ship just like punches through, or maybe that's near the end, but the haze of satellites seems to be what we're going for. Yeah, 6 months to deorbit is really quick. So I don't know how that's economical. I would have thought making satellites and launching them would have been more expensive than, or needing to justify a longer time in space, but I guess it doesn't. So, yeah, so with this supernova, not sure exactly what this will end up looking like, what we'll end up doing with it, but something interesting, hopefully. Otherwise, that'll be a shame. I don't know what this is supposed to be. Funny looking graphs. Yep. Yep, that's my life. Pretty colors. Yeah. So how long? So this is a question for everyone. Let me see if I can get a good example. Give me a moment. Let me pull up a paper I've been working on. It always takes a while to load these things. Okay, this one's probably good enough. Oftentimes, the longest part of writing papers is making the figures. Making the figures, it takes so long. Python is great, but Python doesn't play nice so much of the time when you're trying to plot things. So maybe... Oh yeah, this is a good one. How many, or how long do you think this figure took to make? Any guesses? This will be an approximate guess because I don't dare time how long it takes to make these things. Any guesses? Now this is when I really appreciate the lag between when I say things and the chat. 2 days, that's probably on the upper end, but this is like a good day of work. Is to make this silly little figure. It's insane how long making nice figures takes. So if you're just if you're including all of like the data analysis and stuff that went to make this figure, then that's like months of work. But just making the figure itself, you have the data in hand, it still takes a long time to do it. And it's like, I don't know. I'm pretty particular about my figures. I like them looking nice, so that ends up with me wasting even more time on these things. But yeah, that's a lot of, and you end up with a lot of figures, and you're spending hours on each figure. What I do my thesis on? Do I have it on this computer? Thesis. I think it's on oh, what is this? Why is it? Oh, I do not want this. Scholar. I think this is me. Is this me? It is me. Where is it? I think it's public now. There it is. This is my thesis. I'm not sure why Ireland's publishing it. Let's see if it's... I don't, Oh, no! Oh, no. Why did they... Now, this bothers me. Oh, okay, it changed its name. Good. But oh, man. Because I just named the file thesis resubmission. I didn't know that it would be the PDF file name that they would use for everything. Man, I would have called it something better than thesis resubmission. So this is my thesis. I don't recommend reading it. It's pretty lame. But yeah, The Frontier of Cosmic Cataclysms. That's my title. And it's just a whole bunch of stuff on things. I tried to write it so that everyone would be able to make sense of it, which probably means it's not as scientific as it should have been. But I mean, it passed, so that's all that matters in the end. If you are desperate for killing time, then that is the link to my thesis. And of course, if you find typos and things like that, do not tell me. I don't want to know. I know there are several mistakes in it, which really cut me up, but it's not anything I can do about it now. Sorry, I saw your comment before, but I just skipped by it. Any tips for first year aerospace? I just took a wave midterm. I hated waves, which is why I became an astronomer who works with waves. Tips. I don't know, to be honest. Everyone works differently. So for me, the biggest piece of advice I could give would be to try and find a group of friends to work with. My first year was kind of more challenging because I didn't have I didn't make too many friends in my classes, but once you have a group of friends in the same classes, it becomes so much easier to learn from each other and work from each other. So that's my biggest piece of advice to any undergrad student, is to try and find some people to help you out. Because everyone learns differently, different rates. Some things are easier, some things are harder for everyone. So having a group of people that you can talk with and bounce ideas from is really important. And then if you have time and are interested in doing other things, it's always good to try and get involved in your department. The way I did that was doing lots of outreach, so I would talk to schools all the time, which was fun for me, and people liked that I was doing that. Good night, thanks for joining. I think you said it was like midnight when you joined, so thanks for sticking around for so long. But yeah, so my general advices are find friends, which can of course be challenging sometimes. and also in some capacity try and distinguish yourself from everyone else. So do things that are slightly out of the ordinary, so that people take note of what you're doing, but at the same time, don't put too much pressure on yourself. So, in other words, my advice is mostly useless, but hopefully it helps a bit. And I guess don't worry too much about some things. Oh, hey, thanks for dropping by. I saw your comment about the Greek eyes. I have still to reply to that one. I'm glad you're enjoying the videos. What was I saying? Oh man, I really need more than like a 1 second memory for these streams. So you can imagine how hard it is, how much of a random walk me doing research is if I get distracted way too much. What was I saying? Something about... Oh, right. Don't get too stressed out about grades and things. So, a tale from me is that I never really had amazing grades. I had good grades. I think most of my courses I got like between an A- and an A+ in, so that was good. But there was one course I did where one of my lecturers advised me not to take because it might have been too abstract for me, and I was like, nah, you're wrong, I can do it. But he was very much right. It was way too abstract for me. It was what was it called? Real analysis, which is just the aspect of mathematics, which is proofs, and how do you prove something is true in mathematics, which in principle sounds fine until my brain tried to process it. Then I realized that was my limit for mathematics. So I avoided analysis from that point on. So I ended up getting a C in that course, so dangerously close to a failing grade. So I was really stressed out about that, and like thought, oh, I've just completely destroyed any of my chances of getting PhD or anything like that. But these things matter in the moment, but not so much afterwards. And once you get past your undergrad and move on to the next thing, whatever grades you got before just get erased. Oh man, Central Europe, 2 a.m., 3 a.m. in Finland. Jeez, you guys should go to sleep. Yeah, I did try. Some of the concepts leaked in. I think if I did it again now, I would be much better at it, because programming is very logic-based, and I think my logic skills are a little bit better now. Oh, right, Data Lost, your comment. I haven't read any books by Neil deGrasse Tyson. They're good, I know that much. I think probably his most famous one is the Astrophysics for People in a Hurry. I think that one was very good. Though again, haven't read it myself. Yeah, and there are some pictures in my thesis. Probably the most interesting part of my thesis would be the intro. If you wanted to read that, it'll give you a broad idea of the things that I was working on. I play games on PC. I have a nice computer that I've been leaning on quite extensively over the last year in isolation. And yeah, I've actually been intending to make a while ago I made a video on the galaxy that appears in the sky in Halo 3. That was pretty fun for me to make. And I'm planning to make a video on Red Dead Redemption 2, because there's a mistake in that from an astronomical perspective, which is pretty cool. I at least find it interesting. They do a really good job for most of the things, but this one they don't, and I'm pretty sure it's just for artistic style, which is fine. But Red Dead Redemption 2, I've been playing that so much. It's a fantastic game. It's always good to just like unwind, go adventuring, and that. Is Park Probe going faster than any other spacecraft on April 30th? No, I didn't hear that. So I'll need to look up what's happening with the Parker Space Probe. Yeah. So actually, that reminds me. I've got like 3 ideas of videos that are both weighing equally in my mind. For wanting to make them. More serious videos. I know lately I've been making more, I guess more lazy videos that I can just pump out. What's it called? Yeah, so the 3 videos are, 2 of them are on The Expanse, and 1 of them is on the Red Dead Redemption one. So, I'm planning on putting up a poll today, or today, seeing what people prefer. So the Expanse options are, one of them is it's kind of Expanse, kind of not. It's why we can never terraform Mars. So that one might be a bit controversial. The second one is talking about the ring space in the Expanse, and then the third one is I forget the title I was thinking for that one. It's like an astronomically big mistake in Red Dead Redemption 2. So make sure to let me know which one of those you'd want to see first. But don't worry, I'll end up making all of them at some point. But at the moment, I can only really make a video per week. So one of those will emerge. Do all 3. No, I need to do my actual work though. Is the pain. It always surprises me how long it takes to make videos. It's great fun making them, but boy does it take a while. Like editing. So it's like, I don't know, to give you perhaps an impression of how much time it takes. It's like it'll take me a few days to write a script, because it just takes time to get my thoughts in order. Or that's writing it over a few days, not a few days dedicated to writing a script. So it's probably like a couple of hours to write a script. And then recording. Oh, Night Zast. Thanks for joining, especially at like 2 a.m. or whatever time it is for you. What was I saying? Yeah, so then recording's like maybe an hour or 2, because I can't read and I can't talk properly half the time. And then editing takes so long. I need to get better at it, but boy, does it take time. But that aside, I really enjoy making the videos. Elite Dangerous I haven't played so much. I've played like the intro to it, but I don't have so much time to play games these days, unfortunately. And Elite Dangerous is just a little bit too intimidating for me to get into. I was thinking with the why we can't terraform Mars video to do a game stream, because there's a cool like city builder game about colonizing Mars, which might be fun to play and chat about. Yeah, but the Elite Dangerous looks incredible. Why are you guys watching at 2 a.m.? Go to sleep. I'm grateful, of course, for you sticking around and watching. This has been super fun for me, but 2 a.m. is pretty late. What do I edit on? I edit on iMovie because I'm so lazy. I really shouldn't. iMovie's not so great, but yeah, I think it is Surviving Mars, the game. I have PC. Yeah, 9 a.m. in Australia. That's more reasonable. It's the weekend. Who cares? Okay. Yeah, the Dyson Sphere program. A friend of mine showed that to me, and I thought, man, this looks awesome. So I started playing it. And it's like, oh, the night and day just disappeared. So that wasn't so great. It's a great game, but I got to like I think it's a pretty common point where like the organization just ramps up so much, and I just didn't have time to put into it. But it looks an incredible game, and maybe I'll play. Yeah, I'd be open to playing that on stream as well if people are interested in that. What's this? How did you get to know The Expanse? I got into it because I watched a spoiler-free review of the first season. Yeah, that's a good question. Season 1 was so long ago now that I barely remember. I think this was back when it was on Netflix. So I think I was just looking for something new to watch on Netflix after I exhausted Star Trek for the second time or something like that. So then just started getting into that. Yeah, so if people are interested in just me messing around in games, like that's definitely something that I'm happy to do. It gives me a productive reason, I guess, to play games, which I don't have too much of these days. Yeah, I've also been thinking I should go back and rewatch the first seasons of The Expanse, and because there were interesting points in that which might be fun to make videos on, but my memory ain't so great for things I saw like 5 years ago. Messing around scientifically, that's like the definition of how I live. I don't recommend anyone do this, I certainly won't be. If you like monitored what I do each day, it's just a mess of aimless thinking, aimless doing something, but you know, eventually it culminates into something. So that's good. But oftentimes it doesn't. Yeah, I've thought about streaming on Twitch. In fact, the first science stream I did was on Twitch, because I knew no one would watch it. So there is a Twitch channel for me, but with the first science stream where it's just me talking to myself for like an hour or so to get a feeling of what this would be like. But as for money, I don't. It's better you save your money for more fun things for yourself. I haven't read the book series. I still need to read that. But reading has taken a massive back seat for me, unfortunately, the last few years. Because it's all I do is reading and things for work. Yeah, that's a good plan to rewatch seasons before the new season starts, because there were characters this season. It's like, I have no idea who you are, but I assume you're important. Yeah, it's really exciting. They've been, the next season should be pretty mental, I think. GRBs as standard candles, yeah. Yeah, so there are a few unknowns that we don't, or that exist for GRBs. A lot of unknowns, but they are, they do seem like they could be standardizable because they come in, or they seem to come in distinct camps. So the two main camps are the short GRBs and the long GRBs. Well, the short ones are like milliseconds long, and the long ones are maybe hours to days long. I haven't read too much up about how they can be standardized, so I can't give too much of a detailed answer on that one. As for TESS, it's it can't really see faint objects all too well. So I don't think we'll be using it for GRB cosmology, because there just won't be enough bright GRBs for TESS to do much with. But we will be trying to use TESS for supernova cosmology in the near future. So you're a little bit wrong, but mostly right, so that's good. Yeah, the Uncancel the Expanse campaign was pretty good, and they did get good results. I don't think I have seen Scott Manley's video on that one. His videos are always great. I, of course, like many people, started watching him from his Kerbal Space Program videos, but he makes also really good science videos as well. Yeah, audiobooks, I think those are my way to go at the moment. So I should look into that. Can the accelerated expansion of the universe be due to the warping of space-time from mass as described by Einstein? So the accelerated expansion of the universe is a big question. Big problem question. So what do we see? We measure the brightnesses of supernova at distances away from us. We calculate how bright those supernovae should be on the sky for the distance we see them at. And then we can see if it matches up to what we observe. And we find that it doesn't match up, and that these things can tell us that there is an expansion of the space between us and that object that is accelerating over time. By working out the accelerating over time part, we just look at compare supernovae that are closer to us to ones that are further away. So if we do that, we see the universe is accelerating in its expansion. So the main idea is that there's some mysterious thing called dark energy that's pushing against gravity and pushing the universe apart. That in itself isn't such a crazy idea. There could be such a thing that exists. And in places like galaxies and galaxy clusters, there is just more gravitational, I guess, energy or a pull than what dark energy can push against. So you just have a gravitationally collapsed system that doesn't expand. But I was, in my undergrad, I was taught by Professor David Wiltshire about general relativity and these things. In fact, since I'm back in New Zealand where I did my undergrad, I have some things from that time. So this is, I'm not sure, here we go. This is the general relativity course notes that he made. They're fantastic. I adored them. I've been thinking about trying to adapt them to do some short videos on general relativity. But anyway, he argues that astronomers are mistreating general relativity, and that if you do some different things with general relativity, you can, in fact, explain the accelerated expansion of the universe without the need to invoke dark energy. So he's kind of been fighting the system with that one. But I guess I was young and impressionable, and he convinced me of it. So, so that's that. Yeah, the ether. The ether was supposed to be. So the ether is pretty interesting. It arose, or at least in scientific terms, it arose because if light is a wave, then it needs a medium to propagate through. So there must be a medium permeating space, and let's call it the ether. Then the ether would have some effects, which you could measure. But then it was found that it didn't have, if you did an experiment very precisely, it didn't have those effects that were predicted. So the ether was canned. But interestingly, or at least I think interestingly, the modern view of quantum mechanics, quantum field theory, suggests, it at least seems to me, that it replaces the ether with more ethers, but in this case it's a different phenomena. So quantum field theory says that there are fields corresponding to the fundamental forces that permeate our universe, and particles are just like little ripples in these fields. So if a piece of light traveling through space is like a ripple traveling through the electromagnetic field, which is fine. It does a really good job, and it does okay. So pilot wave theory, that's been a while since I've heard that one. Let me refresh my mind. Oh, pilot wave. This might take longer to refresh my mind than I would like. Oh, hidden variable theory. Yeah, I'd need to reread some things to make sense of the pilot wave again. Sorry, so I'll avoid commenting on that for now, because I will no doubt say something incorrect. Dark matter photo is confusing. Which photo do you mean? Would it be the dark matter web, perhaps? Nope, that didn't work. So let me find a photo of the web. Okay. Is it this photo? What is that word? I don't think I've come across Trinique God? I don't think I've come across that word before. What does that mean? I haven't seen that before. But if it's this image, Data Lost, that doesn't make sense. Yeah, thanks for joining, Kim. 2 a.m. is definitely time to sleep. But I can try and start these streams a little bit earlier for people in Europe, so you don't have such terrible sleeping patterns. Try unique? I'm not sure. Try unique God. I don't know. There are many things I do not know. Ah, gotcha. Right. Dark matter photo. I'm not sure. Dark matter. So I guess, like, as far as my scientific beliefs go, I feel that I have less confidence in dark energy being real than I do for dark matter being real. I think dark matter is probably correct, but dark energy, not so sure. Says the guy who's kind of studying it. Time is relativistic, incredibly so. That is one of the arguments against, or David Wucher makes against the dark energy. So actually this picture is useful. So in space we have dense regions, which are these bright patches, and then we have less dense regions, which are these kind of empty patches. So if you look at it in three-dimensional space, it's like a big cube of Swiss cheese with lots of holes all through it. So the idea is that we have a lot of dark matter in things and gravity takes over, you have gravitational collapse, and then in these regions there's effectively no expansion. But these big areas where there's not so much stuff that haven't undergone gravitational collapse, they'll still be expanding more or less as they were since the Big Bang. So at some point in the universe, or some time in the universe, these big bubbles will start to dominate your line of sight. So if you were sitting here in this central blob and looked out in a certain direction, and you measured how much space was taken up by voids, these big empty patches, and how much space was taken up by walls or galaxy clusters, then at some distance away from you, you would find that there are more, or close to you, that there would be bigger voids and smaller regions of dense material. So then the cumulative effect along your line of sight would be something that looks like dark energy. And inside of these voids, because there's less matter, time ticks faster, because there's less gravitational pull. So they would also expand a little bit quicker. So that's another idea of how you explain the accelerated expansion of the universe without invoking some unknown particle or force in dark energy. So my voice is starting to get a little tired. I don't talk all too much usually, so talking a lot in these streams will definitely puts a strain on my voice. So I might stop soon and get back to doing some work. The article showed that. Oh, which article? Oh no, I don't see your link. That lost. It might be blocking. It might be blocking other people from posting links in chat. Probably for good reason. don't want people posting some pretty crazy stuff. Sorry about that. So the gravitational influence on time is also yeah. So on the surface of the Earth, our clocks run slower than what they do in space because gravity acts to slow things down. The exact reason for how gravity does that, I forget. It's been a while since I've thought about the details, and it's really hard to visualize how these fundamental forces work to slow things down. I can't quite recall, sorry. But the less stuff there is, the faster time ticks. And the faster you go, the slower time ticks as well. So in these voids where there's not so much stuff, then time can tick pretty quickly. And I think it's been a while since I've read his papers, or David's papers, but he calculated what the age of the universe would be for an observer sitting inside one of these voids, and it's longer than what we observe the age of the universe to be, sitting inside an overdense region. So we have, the way relativity works is that it implies that there are 4 dimensions of space-time. So there's 1 dimension of time, there's 3 dimensions of space. So those together make the 4-dimensional space-time, where time is related to space by the negative of the speed of light. So general relativity works with that, and it works really well. So far, we don't know we don't have any evidence to support the existence of further dimensions. But things like string theory suggest that that there are numerous more dimensions. I think like 11 or so dimensions, spatial dimensions. But most of those dimensions will be compact and crunched up into really small things that we have no hope of observing. But there's also another theory. I'm not sure. This probably isn't even answering your question, sorry. I end up usually just ranting about things. The one idea, so of the four fundamental forces, four fundamental forces, gravity is by far the weakest of all of them. And one idea of why that could be is perhaps that gravity is bleeding into some extra dimensions of space that we can't access. So gravity, in principle, would have the same strength as, say, the electromagnetic force, but because most of its influence is, say, draining out into these other places, we only see the weaker gravitational force we get today. Evidence for that is non-existent, but it's a cool theory, and I'm not even sure how you'd go about testing that. It may just be something that emerges from fundamental physics. So speed is somehow mass. Yeah. It's This is another thing I've been trying to remember, how I thought through it myself. Speed is like so you can just think of it as situations where you have high energy, time ticks slower. So the greater the energy density is for your general environment, the time will tick slower. So on the surface of the Earth, we have a larger energy density because the Earth's gravity is involved than what you would in space. And when you're going fast, you have a higher energy density as well because you have the added kinetic energy. So maybe that's a nice way of thinking about how time slows down. It's just where you add more energy. The universe is leaking. I'm not sure. I'm not sure. No one knows the answer to that one. Possibly, but also possibly not. There's one, I guess, on the topic of things leaking and not being nice. In general relativity, energy isn't conserved globally. So that may be confusing. It certainly is to me, because in like Newtonian physics and local physics, energy conservation always happens. It's a fundamental aspect of the universe. But as soon as you expand to from a local picture of general relativity to a global picture of general relativity, then energy conservation just doesn't exist anymore. And the reason for that is something to do with the mathematics. You can't construct a four-dimensional or a four-dimensional killing vector, they call it, which tells you how time would be, or energy would be conserved. So that's a pain. At least I don't like it. Where does the energy go? Who knows? It's not conserved. It just goes somewhere. So one of the things, this is another, I guess, more theoretical video I've been thinking of. I need to find a friendly cosmologist to ask some questions to. But so light that's traveling through space, long distances, will get redshifted, meaning it'll get stretched out to longer wavelengths. So the other consequence is that shorter wavelengths of light hold more energy per photon, per bit of light, than the longer parts. So where does the energy of the photon go as the universe stretches out the photon? Is it just a case that it's not conserved and it just disappears? Or is it something to do with like maybe a measure of the work that the universe needs to do on a photon to stretch it out? So that's a question that's been puzzling me for like a year or so now that I vaguely think about every now and then. So that could be fun to get to the bottom of and make a video on. Good that the time and energy thing makes sense. Yeah, so that's, I'll remember that one for future reference. Universe is a hologram. Yeah, the hologram theory is pretty busted. Like, I don't know too much about it myself, but the concept is that if you can, all you need is like a 2D surface to information on 2D surface to reconstruct the universe by looking at the cosmic microwave background. So that's strange. Isn't it spread out? So you may be right. This again is something that I'm not an expert in. It's just something fun that I've been thinking about with light. So my understanding is, which could be flawed, which is why I need to ask a cosmologist. Photons are just the universe's stretch marks. Yeah, that could well be it. So my understanding is that an individual photon, the energy of that should. So the universe acts on a single photon and just stretches it out. But the energy of a photon is Planck's constant times the frequency, and there might be a 2 pi in there somewhere. So that, and probably a speed of light as well. I can't quite remember. I think it's maybe HC frequency. Yeah, but anyway. What was I saying? Yeah, so changing the frequency of a photon, which is what redshift does, changes the energy of the photon. And it's not clear to me where that energy goes or how it's being changed. There was one, in the early days, there was this idea of like tired light theory, where light just loses energy as it travels through the universe. But that was proposed by fans of the steady state model of the universe, where the universe was steady, fixed, galaxies just sat where they sat, and light, they were trying to explain redshift with this tired light idea, but it didn't stack up to reality, so I'm not sure if it can be applied here. But yeah, I do like photons being stretch marks. Yeah. I saw a comment or a question before. What's work currently? So I have a few things I need to do with calibrating telescope systems related to this paper. So this thing here is like the bane of my existence at the moment. Well, I guess one of the banes of my existence. This is the... So in space, it's mostly empty, but there is some dust in the way that does things to the light that we receive. So if you're trying to calibrate a telescope, then you need to make sense of the dust that sits between us and the objects you're looking at. And there's supposed to be tools available to help you do this easily. But for whatever reason, it's just not working for me. So I need to think through why it might not be working, and send an email to one of the people that has been working on this stuff, so that they could maybe give me some insight into what I'm doing wrong. So that's probably what I'll do at some point today. Oh, and the other fun thing I'm doing today is young stars. I think I posted about it once or twice on the channel. but it's like an outreach group for kids to learn about space. So that's always fun to play around with. So we're going to be doing that sometime today. I think today's topic is the life cycle of stars. So that should be fun. Could it be virtual particles? I know very. So virtual particles are usually used to describe things that don't classically exist in the universe. So virtual particles come in to it when you have virtual particles come in when you have how do I explain this without aggressively using my hands? Virtual particles happen when you have a violation of one of the inequalities, I guess. Now, let me start again. So, 2:30. Yeah, definitely go to sleep. Thanks for joining. Yeah, this has been pretty good. So hopefully we'll do more of these. And if people just want to hang out and are happy to see me mess around playing games, that's certainly something I can do. So I'll put another poll up maybe sometime over the next week for the next stream. What was I saying? Virtual particles, right? So in quantum mechanics, we can never know things perfectly. So there's always a disconnect between various quantities, like the position of the particle and its momentum, how it moves, and there's a disconnect between the energy in a patch of space or of an object and time. So there's a wiggle room window for particles to violate what we would conventionally call limits of reality, perhaps. So virtual particles are virtual in the sense that they can only exist for a finite amount of time. So classically, they don't exist at all. But if you don't include them in your quantum mechanical calculations, then it's just a complete mess. Yeah, and I just see a comment now about the G-2 Muon experiment. That relied very heavily, or this uses virtual photons a lot. 6 a.m. That's super early. Thanks for dropping by. I hope you learned something, or at least had some fun. Let me find a picture that's not my boring paper. Let's go back to this one. What was I saying? Something about the Muon experiment. So if you don't account for virtual particles just popping in and out of existence, then you'll get the wrong answer every time on your quantum mechanical calculations. So they're essential to understanding the universe. So with the Muon result, the reason it's exciting is because it's the first hole that we can see in the standard model of particle physics. So that model is a phenomenal achievement of science, because it can pretty much precisely calculate so many things that we want to try and understand in the very small quantum realm, which is great, but it's also a pain because we know it's wrong on some capacity, but without a starting point of definitely knowing there's a hole somewhere, we can't really find out what the solution could be. So this Muon experiment, by showing that the standard model of particle physics, quantum field theory, don't answer everything, that's a big problem for the model, and it shows us a big hole that theorists can now go and target to try and, I guess, open up into a whole can of worms that might potentially reshape how we understand these phenomena. So that's why that one's such a big deal. And the reason why they think it could be like an extra fundamental force is that the muon interacts through virtual particles with everything in the particle zoo of stuff. So they've accounted for all the things that we know of, and if they still get the wrong answer, then there must be some other fundamental force or particle that kicks in and interacts with the muon virtually on some extremely low probability event, but it still does happen sometimes, which is why we can measure it. So I think the result from that experiment is pretty robust. I don't think we'll see the claims being walked back anytime soon like have done previously on such things, because this was the second time that this experiment was run, and it got the same result as the first time it ran, so I think it's quite likely that this is how the universe works. So we'll see how that really all fits together soon. Hopefully. Maybe not. Yeah, the comment about you don't need to solve everything by yourself is very true. Although, in some ways I'm not so good with that, because I like to understand things, so I get annoyed if I can't work through things myself, which isn't good, and it's I guess a part of the learning process as you go higher up or work through science. You gotta just learn to let other people solve the problems for you. But I'm a sucker for puzzles. Results of the G2 lead to consumer lightsabers. That'd be pretty good. I think my brother was hoping that it would lead to, me as well, hoping it would lead to, like, I don't know, some anti-gravity or something, a way to make a warp drive or travel through space at large distances quite possible. So that's my completely unscientific wild hope, that it might be something like that. But yeah, so there are a few contenders for what this could be. So it'll be interesting to see which one ends up winning out of them all. So I think my voice is getting pretty tired, and I'm gonna need to talk some more in a few hours. So how about we just take some final questions? Don't invent that. Yeah, that'd be we should just defund all of science immediately if they find out the Warhammer 40k warp drive is the way to go. I don't know if we want that reality. I'll accept being imprisoned on Earth over that messed up concept, I guess. It's fascinating, by far fascinating, but also quite strange. So, if you have any final questions, send them to me now, and then I should probably head off and do some of those other things. It's always good feeling the chat lag. Tell us about intermediate sized black holes. So you can have different sized black holes. Dr. Becky had I think it's just released a video recently, in like the last day, on different types of black holes. So you should check that out. But I haven't seen a video yet. Yeah, the 5 types of black holes. Let me post a link to that. Let me post 5 types of black holes. So I'm sure this, I haven't seen it myself, but I'm sure she'll go into a lot more detail and good information. But the abridged version is that primordial black holes are things that are predicted to have been made at the beginning of the universe. We haven't seen evidence of those yet. They may or may not exist. They could be any wild range of sizes, but they're probably the smallest ones. Then you have the intermediate mass black holes, which are the ones that LIGO has been detecting. I forget what the acronym stands for. Whoops. Anyway, LIGO has been detecting these black holes in staggering quantity as they merge together to make bigger black holes. So they're likely the products of supermassive stars that, once they reach the end of their life, either explode in a supernova and then fall back from the supernova creates a black hole in the center, or they just directly collapse into a black hole. So that's the intermediate mass black hole, and then you have the supermassive black holes, which sit at the center of galaxies. And those ones are pretty hard to... those ones are still pretty hard to understand. At the moment, we don't understand how they grew so quickly. So there are theories that suggest that you could make primordial black holes in some environment which quickly gather mass and then they become large. Or you could have some first stars ever made in the universe collapse directly into black holes, and then... actually, did I make a video on this recently? This is ringing some bells in my head. I think I did make a video on this. Let me see if I can find it, on how you can make supermassive black holes. That's how good my memory is. I don't even remember my own stuff. I think it was a while ago, maybe sometime last year. Maybe. Yeah, black hole powered stars, that's it. Let me post a link to that one in the chat. This was a really cool idea when I hadn't come across it before. Oh jeez. Oh, okay. Sorry, give me a second. So I can't remember what this video was like. I think this was when I was starting to get better at making videos, but it still might be a bit janky, as my older videos tended to be. So hopefully that answers the black hole question. What was my thesis covering? Let me see if I can find a link for that. So I don't recommend reading my thesis at all. I don't think that would be a good use of your time. But what might be interesting is if you check out the introduction of it, or the abstract. So that will... I think it's fairly easy to read. I can't remember. There may be some spelling mistakes in it, but... Wow, it's broken. Well, for some reason that I can't post a link to that anymore, but that's okay. I might do a community post later about it, so people can click on it if they want. Is launch of WWT thing? I anticipate most this year. I think so. That said, if the Starship manages to get up into space this year, I think that would definitely be the greatest space achievement of the year. But yeah, once JWST gets up and gets functional, that'll be super exciting. I'm really looking forward to that. I think that's scheduled for like October or August, somewhere around the later part of the year, but we'll see if it sticks on time. Coolest thing the telescope find. What is the coolest thing JWST would find? Personally for me, because I like exploding things, it has the power to see the very first supernova in the universe. So that'd be pretty cool to see what kind of weird physics would be going on with the very first stars that exploded that are just inundated with material. A galaxy person would say something to do with galaxy evolution, I suspect, which is a very interesting topic, and an exoplanet person would say something about composition of exoplanet atmospheres, which is also a very good thing to be excited about. So there's a lot of really nice things that JWST can do, so I really hope it does make its way up and work nice for us. But I think those are maybe the last questions we'll take for now. But this has been fun. I will do another live stream again soon. This seems like it works reasonably well. And it's an entertaining way for me to spend my morning, at least. So yeah, thank you very much for joining me this time. If you want to still ask me questions, you can always send me questions on Twitter. I see it often. Let me just slap that up here. So this is my Twitter. So it's the same as YouTube. Just at Ryan Ridden, you'll find me. Send me whatever questions you want. If I can't answer it, I may be able to direct you to someone who can answer it. Yeah, and I may have a large or some lag time between answering questions that you send me here, because I get distracted by other things. But yeah, thank you all for joining today. It's been great. This has been the biggest stream I've done, so that's nice. Lots of questions, so that's been awesome. Okay, well, catch you all next time, and do send questions my way.